Hello, good morning to all of you. So in today's class, we are going to discuss the 8085 architecture. So in the 8085 architecture, there are a set of identifiable units. The units are interrupt control, serial I/O control, accumulator, temporary register, flag register, arithmetic logical unit, instruction register, instruction decoder, and machine cycle encoding, timing and control unit. We have multiplexer. We have a pair of temporary registers. We have six general purpose registers B, C, D, E, H, L. We have stack pointer. We have program counter. We have increment decrement address latch. We have address buffer, and we have data address buffer. Now, to further elaborate on this, accumulator is of 8-bit in size, temporary register is of 8-bit in size, there are 5 flags represented by 5 different flip-flops. We have arithmetic logical unit which performs 8-bit operations. We have instruction register, which is of 8-bit in size. We have instruction decoder and machine cycle encoding unit. We have timing and control unit. So we have multiplexer. We have the general purpose registers and we have temporary registers. We have the register selector unit that enables selection of the registers from the register array whenever operation is being performed. We have stack pointer, which is of 16-bit in size. We have program counter, which is of 16-bit in size. We have increment and decrement address latch, which is of 16-bit in size. We have address buffer, which is of 8-bit in size. We have data address buffer, which is of 8-bit in size. The general purpose registers and temporary registers are of 8-bit in size individually. Now, all of these units, whenever a microprocessor realizes an operation, collaboratively works with the aid of 8-bit internal data bus. So the communication of data between the various units takes place through the 8-bit internal data bus, and there is a coordination signal sent from the timing and control unit to each and every identifiable units that are there. Now, to further again elaborate on the various units, so associated with each and every unit, you must have observed there are a host of signals that are either sent to or sent from the microprocessor, right? Okay, you see here. In case of interrupt control, there are a host of signals that are associated with interrupt control. So we have INTR, we have INTA, we have RST 5.5, 6.5, 7.5, and trap. You must have observed that there are some signals that are barred and there are some signals that are unbarred. Now, the barred signals are active low signals, whereas unbarred signals are active high signal. Now, what do I mean by that is active low basically means whenever it's 0, it's considered to be high. Whenever it's 1, it's considered to be low. Whereas unbarred signals are active high signals. So whenever it is 1, where it's high, considered to be high. Whenever it is 0, it's considered to be low. So that's the way how the interpretation of the barred and the unbarred signals to be done. Now, you must have also further observed that some of the signals are directed towards the microprocessor and some of the signals are directed from the microprocessor. Now, you see the direction of the arrow basically represents that. So INTR is directed towards the microprocessor, so it is a signal that is sent to the microprocessor, whereas INTA is a signal that is sent by the microprocessor. So that is the way how the signals are to be interpreted. So in due course of time, we'll learn about each and every signal and the role of the various units that are there in the 8085 architecture. Now, let us begin with the description of the roles of the various units. So we have the control unit first. Okay, control unit is responsible for generating signals within the microprocessor in order to perform operations that have been decoded or instructions that has been decoded. So control unit is responsible for generating necessary signals within the microprocessor to carry out the decoded instruction. So whenever instruction is to be executed, it is fetched, it is decoded, and then prepared for execution. So whenever a decoded instruction is to be executed, control unit creates coordination signal so that the operation related to the instruction is being performed. Now, in actual scenario, what happens is that whenever a decoded instruction is to be executed, the control signal enables the opening or closing of the circuitry, that allows for the movement of data to the required position, and so that the arithmetic logical unit performs operation. So in actual scenario, it causes connections between the blocks of the microprocessor to be opened or closed, so that the data goes where it's required, and so that ALU performs the necessary operation. So this is the role of the control unit. So control unit plays a very vital role whenever the instructions are getting executed, because it generates control and the coordination signals. Now, next unit that you have is arithmetic logical unit. So, arithmetic logical unit performs the arithmetic logical operations. Arithmetic operations such as addition, subtraction, and logical operations such as and or, and realization of the and or gate. Okay. Arithmetic logical unit, it makes use of the data that is there in the memory and the accumulator to perform operation. So this we have previously learned, and the result is always stored in the register that's called as the accumulator. So any operation that the any arithmetic logical operation that the microprocessor performs, the result is stored in the accumulator. Now, the registers, right? So you see, this is very much important. The 8085 programming model basically has in it or includes in it 6 registers, one accumulator, and one flag register. Okay, again I'll repeat it. 8085 programming model includes in it 6 registers, one accumulator, and one flag register. 6 registers that are B, C, D, E, H, L, one accumulator that is A, and one flag register that is F, where we have five flip-flops representing 5 different flags. Now, in addition to that, it has two 16-bit memory registers. These are called a stack pointer and the program counter. We'll discuss the role of the stack pointer and the program counter later. The 6 general-purpose registers are used in order to store 8-bit data, and these are represented with the help of alphabets B, C, D, E, H, L. And these 8-bit registers can be further combined in order to create 16-bit registers in order B, C, D, E, H, L. So whenever you want to perform 16-bit operation, the registers can be paired up in the order B, C, D, E, H, L to hold 16-bit data. Now, accumulator. Now, accumulator is an 8-bit register that is the part of the arithmetic logical unit. Okay, the register is used to store 8-bit data and to perform arithmetic logical operation. So accumulator it forms the default operand whenever arithmetic logical operation is performed. The result is always stored in the accumulator, and the accumulator is identified by a symbol by an alphabet A. So accumulator is 8-bit register and is used for and is a part of arithmetical logical unit, and it forms the default operand in all of the arithmetic logical operation, and the result whenever it's generated is always stored in the accumulator, and it's identified by the alphabet A. Now, flag. This is very much important. ALU has 5 flip-flops in it, which are set or reset. Which is set or reset, that means it's 1 or 0. Whenever an operation is being performed as based on the condition of the result in the accumulator, these are set or reset. So ALE includes 5 flip-flops that are set or reset based on the condition of the result in the accumulator. Okay, these 5 flip-flops are 0, carry, parity, auxiliary carry, and sign. 0, carry, sign, parity, and auxiliary carry. So these are the 5 flip-flops that are there, that are set or reset, that is set to 1 or becomes 0 whenever based on the condition of the result in the accumulator. Okay. So zero flag, for an example, zero flag. So whenever the result of an operation becomes 0, then zero flag is set, right? Okay, or it says 0. So for an example, whenever there is a borrow or a carry in case of subtraction or addition, then carry flag is set, right? Okay, whenever the sign of the result changes to negative, then sign flag is set. Parity keeps track of even parity and odd parity. Auxiliary carry, when there is a carry from the 3rd bit to the 4th bit, then auxiliary carry flag is set. So based on the condition of the result, the 5 flip-flops are set or reset. Okay, so you can go through the example here. So if the sum of the accumulator is larger than 8-bit, then the flip-flop is used to indicate a carry called as the carry flag, which is set to 1. Okay, when an arithmetic operation results in 0, the flip-flop called the 0 flag is set to 1. So this is the way how the interpretation of the flags are done. Now, why these 5 flags are important is because most of the instructions that are there defined for 8085 microprocessor relies on these flags for making decisions. For an example, jump on carry, jump on no carry, and these are instructions that works in carry flag. Call on parity, even call. So just there are a host of instructions that are there. If you go through the 8085 instruction set, you'll find there are a host of instructions that relies on the value of the carry these 5 flags. Again, not in carry flag. These 5 flags for making decision. Now we'll move further. So we'll move on to program counter now. Program counter, it's very important to understand the role of the program counter. Program counter is a 16-bit memory register that is responsible for sequencing the execution of instruction. Again, I'll repeat it. A program counter is a 16-bit memory register that is responsible for sequencing the execution of the instruction. Okay, so which instruction is to be executed next? That is the role of the program counter to identify. Okay, so it's a memory register that is responsible for sequencing the execution of the instruction. So the function of the program counter is to point to the memory address from where the next byte is to be fetched. Now, when a byte is being fetched, the program counter is automatically incremented by 1 to point to the next memory location. So this also happens. So the program counter is a 16-bit memory register that is capable of sequencing, or that's responsible for sequencing the execution of instructions. The function of the program counter is to point to the memory address from where the next byte is to be fetched. And when a byte is being fetched, program counter is automatically incremented to point to the next memory location. Now the stack pointer. Now stack pointer is again a 16-bit memory register that is used to point to a memory or read-write memory called as stack. Now stack plays a very crucial role whenever a program includes in it a set of subroutines. So whenever control transfer is to be made to a subroutine, the return address is to be pushed into the stack, and then whenever we need to return from the subroutine to the calling function, then again we need to pop out the content of the stack. So that is the utility of the stack. The stack is used in order to store address there occurs multiple subroutines in a particular program. Now, instruction register oblique decoder. Now, instruction register is used in order to temporarily store the current instruction of the program. The latest instruction that is sent from the memory prior to the execution. So, temporary register is a register, or instruction register is a register that is capable of hosting the current instruction of the program or the instruction that is about to get executed. The role of the decoder is to decode the instruction, that is to create an interpretation of the instruction, what is the operation that is to be actually performed. So once the decoding is done, then it's passed to the next stage. Now memory address register. Now memory address register, what it's responsible for is it is responsible for holding the address received from the program counter of the next program instruction. Okay, so memory address register, as the name says, it's capable of hosting the address received from the program counter of the next program instruction. What it does is that it feeds the address to the address bus. It feeds the address to the address bus of the location of the program under execution. So that's what happens. So the role of the memory address register is to hold the address that the program counter received from the program counter of the next program instruction, and then it feeds the address to the address bus. Then control signal generator. Control signal generator, as we've already discussed in the previous portion, that it is responsible for generating all necessary signal that which enables microprocessor to execute an instruction. It actually enables that the circuitry is opened or closed in order to ensure the passage of data, so that arithmetic or logical unit performs an operation. So that is the role of the control generator. Now register selector. Now register selector. And this is a block that is this is a block block that's responsible for controlling the use of the registers in the register stack. Now, there are various registers in the register stack based on the requirement of the instruction, and the signal sent to the control unit. The register selector switches between different registers. Okay, so that is the role of the register selector. So the block that controls the use of register stack, and just a logical circuit which switches between different registers in the set while it receives instruction from the control unit. So whenever an instruction is getting executed, and if the instruction makes use of the certain register, then the signal is sent to the register selector for enabling the selection of the particular register. Now 8085 bus, okay, system bus. So the buses are basically wires across which binary values are communicated. So across one wire, what we can do is we can communicate a binary digit, either 0 or 1. So typically a bus is buses or communication. These are communication channels established over collection of wires that transmits binary knowledge. So, for an example, if you say 16-bit bus, then we have 16 wires. If there's it's 8-bit bus, then it's an 8-bit wire, because across one wire we can communicate only one binary digit. So across 16-bit, actually across 16 wires we can communicate 16-bit of information. Across 8-bit we can communicate 8-bit of information, and so on and so forth. The 8 wires we can communicate 8-bit of information, so on and so forth. So that is the way how the architecture is being built. Okay, now let us come to the first bus, that's called as address bus. Now address bus, it consists of 16 wires, therefore it's 16 bits, because across 16 wires we can communicate 16 bits. So its width is 16-bit. A 16-bit binary number can be a binary number, that is, a 16-bit binary number can be communicated through these 16 wires. So the possible combination can be 2 to the power possible combination can be 2 to the power 16, starting from 0 to 2 to the power 16 minus 1, because address location cannot be negative. So it's an unsigned number. So if you consider unsigned integer, using 16-bit you can create 2 to the power 16 possible combination, starting from 0 to 2 to the power 16 minus 1. So it will start from 16 zeros to 16 1. So this will be the possible combinations of zeros and ones that you can communicate using the 16 wires or 16 bits. Now, with each and every memory cell that we have a unique address value associated, which is an unsigned integer. So, using this 16 wires or 16 bits, what we can do is we can make a reference to the to the 2 to the power 16 possible address locations. Okay. Now, whenever a particular memory cell is to be selected, then what we do is we place this 16 bits across these 16 address lines, and then what we try to do is we try to select a particular memory cell. Now, address bus or the address values are always to be communicated from the microprocessor, so that's why address lines are always unidirectional in nature. Now, data bus, right? So, data bus is responsible for carrying data to a specified address location once a address has been selected. Now there are 8 bits representing the data bus, so you can create 2 to the power 8 possible combinations using 8 bits, right? Okay, 8 bits. So since the data is communicated to and from the microprocessor whenever operations are being performed, data bus is bidirectional in nature, right? Now control bus are lines that are used for sending and controlling and coordination signal from the whenever an operation is being performed by the microprocessor. For example, read, write. Okay, yeah, depending upon the requirement, what we can do is we can send necessary signals through the control lines and make microprocessor do the responsible task. So this is the way how the control bus basically works. So control buses are responsible for carrying controlling and coordination signals from the microprocessor to the memory devices. So some of the control buses are unidirectional in nature, and some of the control buses are bidirectional nature, right? So it's basically used for coordination activity. So in today's class, what we have learned about is we have learned about the basic architecture of 8085, microprocessor, right? Again, we have discussed the various identifiable units, the associated signals. The associated signals will be discussed in the next class, whenever we will be discussing the pin configuration of 8085, because there also we need to discuss the associated signals. We have just learned about what are the various identifiable units, and we have discussed the role of the control unit, the arithmetic logical unit. We have come across the programming model, which includes the various registers. We have discussed the role of accumulator. We have discussed the roles of the various flags. Then we have discussed the role of the program counter and the stack pointer. Then the instruction register decoder. Then memory address register. Then we have discussed the role of the register selector, and then we have discussed the various 8085 buses that are there, and the size of the buses, the capability of the buses as well. So in the next class, we'll be discussing the pin configuration of 8085, wherein we'll be discussing all the signals that are being listed in the 8085 architecture. So thank you very much.